ratio and Weil-Petersson volumes.
Thanks everyone. First of all, I'd like to thank the organisers for putting this together and inviting me to speak, which they don't regret. It's been fantastic so far. I guess I've come from Melbourne, Australia. When you come for a 5-day workshop and it takes approximately 60 hours of travel there and back, it does make you think, am I getting value out of this? And I have already, so thank you, thank you. I want to talk about some work in progress. This is sort of a collaboration in the family, so to speak, with Paul Norbury, who many of you will know, who was my PhD supervisor many years ago, and also Arlo Taylor, who's my PhD student. Just to give you an idea of how in progress this is, Arlo started on Monday last week. So, when I was deciding what to talk about, I thought this would be a good topic because it's something I learned about, I think 1 year ago to the day in this room. And was presented to me by Alessandro Giacchetto. So I'd like to start with a picture he showed us. So I call this Alessandro Giacchetto's magic square. It's really a tale of 4 spectral curves. So Alessandro drew this picture and he said, there are some spectral curves that we all know and love. So one of them is airy. We've heard about airy many times this week so far. It looks something like x equals half y squared, something like that. And it does something magical for us. It calculates what I'll call Timosevich volumes of the moduli space of curves. This is not yet compactified. And many of you will know that this sort of reproduces psi-class intersection numbers on the Delay-Mumford compactification. Okay, so that's at the bottom of this square or diamond. What else do we have? Maybe I'll draw something over here. And this is a sort of well-studied spectral curve, but I'll use Norbury's viewpoint here, that there's this spectral curve which enumerates lattice points in the moduli space of curves. Okay, over on this side of the magic square, I'll talk about a spectral curve that we've already seen this week. It was mentioned by Bertrand and written about by Bertrand and Nicolas. And this is the one that looks approximately like y equals sine the square root of x, something like that. And this one produces for us the Weil-Petersson volumes of the moduli space of, in this case, hyperbolic surfaces with prescribed boundary lengths. G, of course, refers to a genus. Okay, and somehow, what do these arrows here mean? It means that you can recover area from these 2 pictures, and that shouldn't be surprising from the topological recursion perspective. You recover area from many curves, although somehow there's a very sort of direct, sort of geometric picture here. These sorts of volumes come from some piecewise linear structure on the moduli space of curves, and somehow that sort of volume sort of splits into sort of these polyhedral pieces, and this lattice point count is somehow some approximation to that volume calculation. Here, this is some sort of deformation of that away from the piecewise linear structure towards some symplectic structure, and this sort of arrow you can think of as looking at sort of large L, because there's an L in that picture. You just scale up all those boundary lengths, and over here I might call this large, the analogue of L here is B. B is going to be a positive integer, L is a positive real number. Okay, but the thing that I sort of learned about from Alessandro Giacchetto is the thing that he drew up here, which is this sort of spectral curve written down originally by Okuyama. And this calculates for us correlators in the double-scaled SYK model. Of course, feel free to stop me at any stage if you have any questions. So this this model has some sort of parameter involved. You could call it lambda, or I'm going to use q, which is e to the negative lambda. And so very directly, these two spectral curves, you can visually just look at them and say, well, when I set q to be 0, I recover this spectral curve here. So that one's sort of absolutely clear. There's something which is a little bit less clear. Maybe I'll make this a little dotted arrow. And this is some sort of limit as q goes to 1, which is not as direct to see. And this is something that Okuyama sort of saw, that there's this connection between these double-scaled SYK correlators and the Weil-Petersson volumes, and verified in some small genus and small cases. And so I would like to speak about maybe this arrow today.
So upstairs you have also the B's and the L's, or there are no...
Upstairs are going to be some B's. Yeah.
Okay.
Yeah. Okay, so let me first talk about, very naively, the double-scaled SYK model. So many of you will know about this, and I'm sure many of you will know a lot more than me about this, but I'd like to try, as Leonia did before me, to make this understandable. He claimed that his talk was understandable to high school students. That sort of showed me that Russian high school students are probably more advanced than Australian high school students. Okay, so first, what does SYK look like? So what we do is we start by taking some even integer, positive, and we take n Majorana fermions. So what that means is we have psi 1, psi 2 up to psi n, and they satisfy this very simple anti-commutation rule. Some of you will know about the work of and life of Majorana. It's something that is discovered relatively recently. Majorana was an amazing theoretical physicist from the early 20th century. What I discovered more recently is that he disappeared off the face of the planet when he was 31 years old in 1938. And then a relatively recent investigation that ended in 10 years ago, so many years after his disappearance, found that he probably ended up in Venezuela and was there in the 1950s. So, incredible story. So, with these Majorana fermions, we introduce this Hamiltonian. So this is I squared root of -1. Then I have these i's here. I choose some numbers, p of them, from 1 up to n. In order, I have this random cluster.
So isn't this just Clifford algebra? If 0, then I would agree, but
Yeah.
this way it is Clifford algebra.
Yeah, essentially.
Excuse me, just what is the context? You have a manifold, or you just have...
No. So these are just operators acting on like the Fock space, just some finite dimensional vector space of
What do you code Majorana?
that comes from this. It's some sort of real vector space. Okay. So I have these sort of random couplings, which are called J's, sitting next to these fermions. And we choose these random couplings as some sort of Gaussians. These are IID Gaussians with mean 0 and sum of the variances is 1. Okay, so you can work out each variance is 1 on n choose p. Okay, so that's the sort of vanilla SYK model, sort of rather well studied. It's rather simple. It's a quantum sort of toy model that happens to demonstrate a lot of physical phenomena like quantum chaos, holography, strange metals. So it's been sort of a quite useful toy model. In more recent years, people have been interested in this double scaling limit. Okay, and here, so we've got these, this choice of P, we've got this choice of capital N, and now we'd like to send them both to infinity. And it turns out that the sort of natural way to do this is to let them sort of scale in the following way, where we want essentially want P squared on N to be constant. So let's call lambda this this expression 2p squared on n, and we want this to be fixed. I use quotation marks here because, lambda could be irrational, for instance, and we don't necessarily want to fix this. We want this p and n to sort of, this ratio to approach lambda. Okay, and so what would a natural question be? Of course, you might ask for correlators. So you can ask what is something like this at large n. Here, I'm going to usually stand to put a little j here to just emphasize that we're sort of averaging over these Gaussian couplings.
Sorry, the trace means you take a trace over the
Fault space.
Okay. And then the bracket means you take average over J.
Exactly.
Oh.
Exactly. So you might wonder, how could I convince you that this might be an interesting problem? There's some sort of basic results which might suggest that there's some interesting combinatorics underlying this. The first thing I'll say is that there's this obvious statement here that if you take an odd power, this will give you 0. Okay, it's just you taking a product of an odd number of Gaussians with mean 0. Okay, of course more interesting would be if we took an even power here. Okay. And so I'd like to tell you what...
Sorry, before the limit.
Sorry, this is in the large n limit.
Yeah, okay.
In the large n limit. Yeah. And here in the large n limit, what do we see? We see this beautiful sort of combinatorics arise into sum over objects called chord diagrams. Even without me telling you what a chord diagram is, you could probably guess. So the sum over k chord diagrams, and we write down here q to the number of intersections, where here q is secretly hiding my parameter lambda. Q is e to the negative lambda. Okay. So let me show you what this looks like with an example. If you wanted to know, for example, the trace of h to the 6, what is it? It turns out to be q cubed plus 3q squared plus 6q plus 5. The reason being, if we're using this result, what we want to do is take a circle and draw 3 chords that connect 6 points in pairs. If everything went diametrically, then what we see is 3 intersections. And that gives you your q cubed. If we sort of draw this diagram here, we have this times, there are 3 rotations of this diagram, and this, because there are 2 intersections, it contributes, each one contributes q squared, that's your 3q squared, so you see the picture. I'll just draw the rest so that you can verify that you understand what's going on. This one would have 6 rotations. This one would have 3 rotations. And this one would have 2 rotations. So at least it suggests that there's something nice going on. And I think if you thought about it for a little bit, maybe you wouldn't immediately sort of write down a proof, but you could convince yourself that this is true. What are the chords? I mean, this is saying that we have 6 of these Gaussian couplings, and by Wick's theorem, they'd have to come in pairs. Okay, and why are they around a circle? Well, because we're taking a trace. Where does this parameter e to the negative lambda come from? Well, now you're wondering, when you take, let's take, there's a random coupling here, a random coupling here in the recall, and when you try and sort of move them together, when you try and sort of use this anti-commutation rule to move them together, you're going to pick up some number of negative signs along the way. And basically this is going to somehow measure the number of negative signs you're going to expect. Okay, something like that. And this critically uses this scaling, e squared on n. If you use some sort of other sort of power scaling, you sort of wouldn't see this beautiful picture arise. Okay, so hopefully you're convinced there's something interesting going on from a combinatorial point of view.
Can I ask a question? So in
Please.
the left diagram, if I squint a bit, I may see how many intersections?
This one?
Yeah.
So this is 3 intersections.
Okay, this is 3.
It is 3. It is 3. So
It's a triangle. Okay.
yes, you must draw with a bit of randomness. Okay. So basically, intersection is just formed when you have two chords whose endpoints alternate around the circle. Okay. So from this, I'd like to introduce Okuyama's spectral curve.
There is no explicit formula for any n.
For fixed n?
Yeah. Or generating function, for example.
I'm not sure. It wouldn't be too difficult, I think.
Sorry, what was the question?
Sorry, the question was for fixed capital N, can you say something?
No, for just, well, you wrote trace h to the 6, but trace h to 2k just for any k.
Oh yes, sorry, so that's this.
Yeah.
So it's in general this number.
Yeah, but if you can just explicit this for this sum. Write this sum explicitly.
As in, what is this polynomial you're asking?
Yeah.
This is a polynomial. What is the polynomial? There are ways to do it. Sort of people in analytic combinatorics have sort of discussed this for many, many years. It's in the online encyclopedia of integer sequences, of course. And then I guess you can get from the spectral curve, as I'll show.
I see.
I mean, the leading
Current
order is the
relation.
Catalan number, right? The leading order is the Catalan number.
This one?
Yeah.
This is
Catalan
yeah.
number. And then you have higher genus Catalan numbers, which can be constructed by topological recursion with just one boundary gives you these numbers.
Not quite.
Why? The next one? Okay, maybe not.
Not quite. So the sum of these is going to be the double factorial. So it's 15.
Yeah, which is the number of permutations. Yeah.
Yes. So I'm not. Well, I guess there are many things you might call high genus Catalan numbers,
Okay.
and you're welcome to call these high genus Catalan numbers. I will not. Okay. So the spectral curve is something that sort of looks quite nice, I would say. So here's your x, a very familiar x, and then here is your y. So there's a half. There's a z minus 1 on z. And then we need some q's to arise, and this is how they're going to arise. I'm going to take this infinite product of 1 minus q to the I z squared, 1 minus q to the I z to the minus 2, and we divide this by 1 minus q to the I all squared. It should be sort of reminiscent. I mean, this sort of product, comes from the Jacobi triple product formula, so there's something sort of nice going on here. And what we'd like to do is feed this into machines with recursion. Anytime someone gives you an x and a y, I think there are some of you who would just do this automatically, right? And so what do you get? You get these multi-differentials, of course, which, if you expand in the z's, will give you some coefficients. So I'm going to call these coefficients ngn. I'm going to put a little q to remind me that there's a dependence on q. Okay, and these take these integer parameters, and then this is somehow just some generating form. So just bi zi to the bi minus 1 dzi. Yeah. Okay. So there's nothing sort of, I think, hopefully unnatural here, but there's a lot hiding in here. So this is going to be some function of q, typically. Okay. So one could ask, where did this come from? And it's actually...
Sorry, then this number, this is not, it's a series, right? It's not the, it's not like polynomial in differential, right?
This is a series, yes. The b's go up to...
You're really expanding at 0, not at
Expanding at
ramification
0.
point.
That's correct, yes. Expanding this at 0. Kento has observed the branch point, ramification point, whatever you like to call them, of this spectral curve at 1 and negative 1, expanding away from that. So you could ask where this comes from. I guess it comes from the observation that if you take the ds SYK model, and then we know something about what happens in the sort of planar world, I guess it was sort of written down that this is governed, well, possibly conjecturally, I'm not sure about the status of this, I guess it's in the physics literature, governed by some sort of matrix model, and it's just a one Hermitian matrix model with some, not polynomial potential, but some sort of infinite series potential, which essentially looks like this. And the way that you cook this up is really just to observe, can I write down some one Hermitian matrix model that reproduces these moments? So if you can do that, conjecture, this matrix model reproduces more than just these moments, okay?
Can I ask you something? So if you have like the 2-point function there,
Yes.
what kind of diagrams you draw on like a cylinder, and then you count the crossings, or?
Good question. Yes, there is a theory for what these chord diagrams look like on a cylinder. It's not expressed exactly like that in the physics literature, but as far as I know, no one's written something very explicit and combinatorial that goes beyond that. So it does look like some sort of combinatorial count with these intersections, but I don't know if it's known beyond 0, 2.
So I just wanted to clarify. So for you're saying like if you take a matrix model with this potential and then compute the moments and take the double scaling limit, it would coincide with this formula?
Yes.
Okay.
Yes.
Is it conjecture or is it like proven?
That part's known. That part is known. Yeah. So what's not known is whether you can reproduce higher things.
Norm, what is this N, G, and Q? So it's not.
It's a function. So this is a function of the bees. So you give me your favorite genus. You give me some positive integers b1 through bn. I'm going to give you back some function of q. Yes, that's not.
Excuse me, well, in principle, omega gn should have poles at branch points, that is at z equals plus or minus 1. And here you do an expansion at infinity.
How it's related
This is the
to
expansion at 0 or infinity, yes.
Yeah, okay.
Yes.
how it's related to number of integer points?
Number of.
Integer points.
So if I set q here to be 0, this all disappears, this product. Okay. And then this q would be a 0. Then I would recover what Norbury calls the number of lattice points in the moduli space of curves, which is essentially counting some form of ribbon graphs. I will hopefully say more about that at the end, as long as people don't interrupt me so much. No, it's very welcome. The ending's terrible, so more interruptions are better.
So if you put Q to 0, you said, right? It's
Yes.
just like the Gaussian interior sum, which
Yeah,
is...
exactly.
Yeah.
Okay, so this is somehow, in some sense, cooked up naively, this matrix model. And then, of course, once you're in this matrix model world, Akiyama was one who first decided to try and throw the tools of topological recursion at this. Okay, so that's somehow the idea. And then the conjecture then would be something like the following. So if I wanted to sort of take some multi-trace correlators, they should be expressible in terms of these NGNQs, whatever they are. And it looks a bit interesting. It's not supposed to look interesting, but I've done a sort of renormalization that makes it a bit more interesting than it should be. Okay, so it looks like this. There's this infinite Q Pockhammer symbol to the cube. Here's your large N expansion. Okay, and then we get essentially this. So the sum over the V's, this quantity NGNQ of the B's, I'm running out of space, and then some extra sort of contribution kicks in here. I equals 1 to n, bi times some modified Bessel function. Running out of space here. Not too important. All I want to say is that I guess this object here maybe shouldn't look too unfamiliar to some of you. This will be something like a discrete trumpet, as we saw the trumpet in Ilya's lecture previously. So maybe a discrete version of the trumpet. Okay, great.
architecture is the missing part is that you don't have this similar expression for this product of these traces for the matrix because
More than that, I'm also saying that there is a large and genus expansion. So it's not just the genus zero terms. So when I say it's a conjecture, it's not necessarily written down as a conjecture. In Okuyama's paper, he writes that, and I quote, "It is tempting to speculate that this is true."
So this is in a double scaling limit.
In the double scaling limit, so every time you see like a P, you can write in terms of n, that sort of absorbs some of the n's, but there's still going to be some n's left over, which will give you your genus expansion.
Yeah, this is then your H bar in topological recursion.
Exactly.
Okay. So you have a precise connection between N and Q and H bar in from topological recursion perspective. So if you define this as your H bar, then there's a connection between N and Q and H bar.
Yeah, and this will be some free energy.
And does this also mean that Y in the spectral curve depends on H bar? Because, okay, just one over, okay, maybe not, yeah. Because N can be 1 over H bar. Okay.
Okay, so you're probably wondering, you may be not wondering, what does this n look like? So if I say I wanted to give you something like n genus 1 with 2 integers fed in here, and there's this q dependence. I write x here, this is an example, but I think it could also be an exercise if you wanted to treat it as an exercise. And this is what it is. So it's going to split into cases. In the first case, I'm going to get a to the 4 plus b to the 4 on 384 plus a squared b squared on 192 plus this thing, which I'm going to call z to q of 2. I get 8 of those minus 1, or 132 times a squared plus b squared. And I get 5 on 2 z to q of 4 plus 7 on 2 z to q of 2 squared minus half z to q of 2 plus a half. And I get that when a and b are even. And if you could predict that, I think you're doing quite well. And then you get exactly the same thing essentially, except this changes. This would be 5 on 96 when a and b are odd. And then when a and b don't share the same parity, you just get 0. Okay. So that gives you an example, and maybe a priori you wouldn't have said that that's what it should look like. Here's a fact. This was observed, I guess, by Okuyama. I'll call it fact A. This object here, which stores all of these double-scaled SYK correlators conjecturally, essentially looks like a polynomial, except it depends on the parities of the arguments. And so that's commonly called a quasi-polynomial. Furthermore, it's not just a quasi-polynomial in the arguments, but you only see the squares arise. We've got some sort of control here over the degree, 6g minus 6 plus 2n, which would be a sort of familiar expression for many of you. And we can say something about the coefficients as well.
Excuse me, what zeta q? What zeta p and zeta q?
Oh, yes, I will say that. I should definitely say that. It is true for some zeta q, let's say. And the coefficients live in, they're all polynomials in these zeta q's, which you don't know what they are possibly. Even if you think you know what they are, it's possible you don't. It's a quantum zeta function, but there are many q zeta functions around. And so here, I want to set zeta q of, and I'm only going to tell you what it is for even integers. This is a sum. And under here, you put q to the ion 2 minus q to the negative ion 2. Some people would call that a q integer. A q integer sort of that replaces I. And so this looks like some q version of a zeta function. You know, if you do it differently, you might have some power of q up here and you'll get a different thing. That's not what I'm talking about. Okay. And I guess one thing I want to say about this fact is, you know, if you go back and you look at what topological recursion, you know, what it looked like when it was originally written down, you know, none of this like log TR, generalized TR, refined TR, super TR, none of that. Just the original object. This thing was supposed to be a rational function, right? So I'm living on a genus zero spectral curve. This should be a rational function. When I look at it, it doesn't look rational to me. This product up to infinity somehow throws a spanner in the works. So if you really want to do this carefully, you probably should say something about it. So this is what I'm going to say. Everything I say sort of remains true when the product in this expression for y that we see on the other board and the sum in the definition of zeta q are truncated to whatever level you like, to some positive integer, I don't know, to some m in z plus. Okay. So, oh, I'm only going to take, you know, there's a sort of reality to doing this. Say you go to, you know, GitLab and you want to type in your spectral curve. You might actually just decide you wanted to truncate this. Yeah. And similarly for the q zeta function, it just happens that the truncations match. You know, so you do the whole thing and this m just stays the same.
No, for the moment q doesn't take any value. Is there, so if I look at q equals to 1 here?
If you look at q equals to 1 here, that's very bad.
You want to do that later on, no?
Yes, and that's why I rubbed out the board, but you might have seen there were quotation marks around q equals 1. It's really, we're going to take some lambda goes to 0 limit. Okay. Yeah. So in this lambda goes to 0 limit, this would essentially look like some power of lambda times this, the usual zeta function plus, you know, plus corrections. Yes, no, don't go setting q to 1. Especially if you look at the spectral curve. You know, it's not nice. Okay, the other observation that was made by Okuyama, so Okuyama calculated several instances of this. You can find this particular formula I've got upstairs there in his paper. What he did, which I'm not sure, well, personally I'm not sure why someone would do this, but this is what he observed, is that if you take this quantity, but we're going to sort of scale up the entries in a particular way. So we're going to look at a limit as lambda goes to 0. And then to accommodate this, I want to multiply this by lambda to the 6 minus 6 plus 2n. If I do this, then I see the Weil-Petersson volume. So it's VGN L1 Ln with some factor out the front, which is sort of not too important. Just some power of 2.
What do you mean by fact?
Sorry, what do I mean by this? What do I mean by it?
No, fact. Like,
oh, fact, sorry. It's known. Okuyama observed this for some cases. Maybe some people tried to prove it, I tried to prove it, and yeah, we can prove it. Yeah. I mean, I haven't seen them in the literature, but I guess this is our sort of work in progress. It's not yet on the archive. Okay, so for those maybe who aren't used to seeing this sort of expression, this is the Weil-Petersson volume.
So where's Q? On the left-hand side you have a Q.
Yeah, so Q is e to the negative lambda.
Right.
Yeah. So really you can think of fixing this m where we're truncating everything, then taking the limit, and then sending m to infinity, and then this is what you'll get. So this is a very quick volume of the moduli space hyperbolic surfaces with prescribed boundary lengths. Okay, so it has this beautiful symplectic form, which sort of touches on what Leonia was telling us about in the earlier talk today. And then we know that this is a polynomial with coefficients that have to do with pi squared. And there's a polynomial in the squares, in fact. So I guess if you know this, and you see this, maybe it's not that crazy that you'd expect them to align, I don't know. To me, I wouldn't have known to look. And I guess I want to sort of mention this is known because of the fascinating work of Mary Mizukami from around 2007. Okay. But I think once you see this, it should be clear how to proceed, because it's not. Here we have topological recursion, and what I want to do is tell this as an example of some sort of basic setting where topological recursion can tell you quite a lot. So all we need to do now is really try and compare this quantity n with this quantity v. We know these are generated by topological recursion, but we also know that these v's are generated by topological recursion. So this is a fact. This goes back to, I believe, Bertrand Nicolas, also from around 2007, which is that if you take the right spectral curve, and I'm going to write this in terms of t, maybe it'll be clear why I'm using a different parameter here later. This t squared, and then y of t we take to be 1 over 2 pi sine 2 pi t. And then you run your topological recursion, then we get these multi-differentials. I'm going to sort of just remove the differential part for now. And these are essentially the Laplace transform of these Weil-Petersson volumes. So there's this multiple n-fold integral, VGN, L1 to Ln, and then we've got this Laplace kernel, so Li e to the negative ti Li dLi. So I guess all you have to do is stare at this and stare at this and say that they're essentially the same. So really, and when I say stare, you're actually doing the opposite of staring. You're sort of like trying to sort of make your vision go a bit sort of blurry until you see it. And so that's, I'll show you what that looks like.
So there's an equality. Omega gns is equal to the integral of the volumes.
Sorry, thank you. Oh, I did have an equals, didn't I? And I got rid of it. Thanks. Okay. Any questions?
Are you going to show that the limit commutes or something? Is that what you want to do? Are you going to show that the limit commutes with this procedure? Like if you take the naive limit, if I really take the limit of fact B for omega gn of this Okuyama curve, you probably don't get what you have to get.
That's not. You could try and do that. I mean, I think it would.
Do you expect that to be true?
Probably. You'll see what I say.
Yeah, sure. Thank you.
Okay, so let's talk about fact A. So I want to convince you that we see this appearance of these z to q values when we write out these polynomials. Okay. First, I should probably try and convince you that you actually do get polynomials, and this is sort of just using some very basic observations around the topological recursion, so general observations. So if you have this particular x being z plus 1 on z, you have this rational spectral curve, and then you have some control over the poles. So these omega gns have poles only at the branch points. And you also have some control over the order. Well, if you give me some sort of rational function with only, or some rational differential with only poles at the branch points, and I try and expand it to z equals 0, the coefficients are going to be polynomials. If you've got poles also at -1, then you're sort of going to get polynomials multiplied by like powers of -1. So when you put it together, you get this quasi-polynomial. So this is enough to tell you that at the level of coefficients, this is quasi-polynomial. And we have some control. The order here looks a bit like the degree, but there's a shift. Okay, so just some very sort of general statements around topological recursion sort of already tell you that you get these quasi-polynomials. What I don't know yet is that they're quasi-polynomials in the squares, which is what I promised. It turns out that they are. With spectral curves of this particular form, we know from general reasoning that if you write up one of these multi-differentials, but then you apply the local involution, you have some sort of nice structure at that particular branch point. Here I'm applying, there's an involution here, z goes to 1 on z, and when I apply it, in this particular case, I'm always going to get 0. So they're just negatives of each other. There's an oddness going on. At the level of the coefficients, it turns into an evenness property. So this is actually a quasi-polynomial in the squares. Okay.
Before you raise that one,
Yeah.
so something has been troubling me from the start. Like in y of z, there is an overall factor, which is the denominator, and it's squared.
Yeah.
And in the conjecture, it's cubed.
Yes. Yeah.
But it seems like you need at least one of those factors to have the zeta q's have finite limits.
So in all the things I'm doing, I don't have this factor. This just arises when you want to look at the correlators. The difference between the square and the cube arises because this should actually be all multiplied by this thing cubed. It should be a triple product, just the Jacobi triple product formula.
Oh, z squared, z minus 2, and z to the 0 divided by the cube or something like this?
Yeah, so you could remove this and replace it with a 1 minus q to I up here, for instance.
And the third one.
And then it would kill this.
Sure.
I'm just wanting to connect directly with Miyazakani, so to do that, I need to put this denominator in instead. That's all. Okay, so everyone's memorized the spectral curve, that's great. When I started going to conferences in topological recursion many, many years ago, every single talk started with someone writing down the formula for topological recursion. And then in something like, I don't know, October 2014, everyone decided you would never write down the formula for topological recursion ever again. Kohei somehow went against the grain and decided to do it this morning, but I'll write down something like the topological recursion for you. Okay.
Yes, but he did it in advance.
Yes, true, yes. It used to be, you'd have, the first 10 minutes of every lecture was just writing down the topological recursion. Okay, so what I want to say is that the TR formula, so I'm not going to write down the whole formula, but I'll write down most of it. I'll just say it expresses each of these differentials as a sum of its principal parts. Principal parts meaning, you take the wrong part of, you look at the poles and you take the wrong parts. At every pole, you're going to get a little wrong part. You sum them all up, you get omega GN. Okay. So, what does this tell me? It means that I can sort of, it means that I can write down very explicitly, at least let's say in the case x of z equals z plus 1 and z, and as long as your y is nice enough, let's say under y of 1 of z equals negative y of z, which is what we have in our particular scenario, I can write this. So omega gn of z, and they've got a whole sort of n minus 1 other z equals, and I sum over the branch point. In this case, we've already observed that they happen at plus or minus 1. There's some principal part here, and then I write down, there's a sort of kernel. This is 2y of z, x prime of z. the derivative of x, and then the jump that you're used to seeing when you write down topological recursion. So here, I would have omega g minus 1, and oh, there's a minus sign here. N plus 1, z, zs. And then I've got this big sum where I'm sort of splitting the topology. So omega g1, z, zi, omega g2, z, zj. And then here, to make this recursion, I don't allow 0, 1 to rise. I don't want omega 0, 1 in there. If it does, I just ignore it. Okay. And I take this principal apart at z equals alpha. So I add 1 and minus 1, and I sum them up, and that's what I get. So this is the topological recursion. Okay. Well, I've just done a little bit of the work for you. Okay. Now, what we want to do is compare that to the curve that stores the Weil-Petersson volumes, and that takes this form. So we've got x of t equals t squared, y of t, it turns out to be some odd function of t in sine. And then in that case, we get something which I'll write as follows, ts. Now there's only one branch point when this derivative vanishes, so it's at 0. So I get this principal part, negative 1 over let me abuse notation. I'm going to write y of t, x prime of t. I know there are some of you in the audience who think this is terrible. This x and y, not these x and y. This one has z's, so it means it's coming from the Okuyama spectral curve, and this one has t's, which means it's coming from the Weil-Petersson volume spectral curve. Okay. I could adorn it with extra letters, but hopefully you understand. And this bit is almost exactly the same. So almost the same. So with z's replaced with t's. It's not the same, and this we're taking this at t equals 0. So why isn't it the same? You know? It's not, you do the calculation, it shouldn't be exactly the same. It's not. Sorry, I lied, sorry, it is the same. Sorry. Sorry, I'm using an old version of the notes in my head. This is the same. Okay. I'm good for time, so 12 minutes. Okay, 12 minutes. Okay, 13. Probably 13. I'll probably start doubling my speed as we go along. I think we'll fit everything in. Okay. So it turns out, okay, so when it comes to fact A, I sort of really, you know, we're working at the level of the topological recursion. You really want to turn this statement about coefficients into some statement about these differentials that arise. And it's sort of not a complicated transition. All you need to know is that when we try and sort of write this out, we're going to get, we know we're going to get things like dzis. We know we're going to get poles at zi equals plus or minus 1. That's what this AI are. And so what I need is these k's, and there's some integers, and there are actually at least 2. These a1 through an have to be plus or minus 1. And it turns out that if you like, you can sort of try and add some sort of bound on the pole order here. So we want the sum of the ki's to be at most 6g minus 6 plus 4n. Yeah, that's it. Okay. And all we really want to do to guarantee that these zeta q values appear is to say that whatever goes in here is some polynomial in the q zeta values. I guess this, some polynomial that depends on a1 through an and k1 through kn. Okay. So we want this to be some sort of nice polynomial. That's all. So if we can prove this, then we're done. And then once you look at the formula, it should be reasonably clear that you're going to proceed by induction, what you need to do that, well, you need to check the base cases, of course, which do have to follow the structure. And then what you want to know about is, if you look at the formula here, you want to know about this 1 over 2y x prime. Okay. Because really, the structure is going to say, well, everything else is essentially going to work for us, and we just need to know how this is going to contribute. Okay. And it contributes in a very sort of nice way. So it turns out that this is, so there's some sort of junk out the front, which I'm not too concerned about. And then I get this exponential, let's see, of this sort of linear contribution in the zeta values sitting in front of these powers of m. Okay. And of course, if you want to do this correctly, you've also got to do this at -1. I guess you could say it's the same, but you write b here instead. Plus 1 for n. And these a's and b's are very explicit, so you just calculate them. If you need to, you just calculate them. And then essentially what you're doing is you're computing the topological recursion, and that's enough to know that you're going to get these q zeta values. So that was called fact A. Fact B was something about these Weil-Petersson volumes. So we want to see these Weil-Petersson volumes arise in the limit. And so if you think about what it means to take this lambda goes to 0 limit, right, so I rubbed out what we meant, but let me tell you what it means. You take, you sort of look inside this quasi-polynomial that you have, and you collect the top terms. Now, top is not top in the sort of polynomial degree, necessarily. What you need to do is you look in there, you know because of what we've said upstairs, we know we've got these q zeta values arising, and what top means is that we want the b degree plus the zeta degree, where you would say like the degree of this zeta q of 2k is just 2k, it's just the argument. So we need this to be as big as possible, and the biggest thing could ever be is 6g minus 6 plus 2n. Okay, so that's the first thing you do, and then in the process of taking the limit, you then replace the zeta q of 2k with zeta of 2k, and everyone hopefully knows that this has some sort of nice formula. So this is a Bernoulli number, and then there's 2 times 2k factorial here. Okay. So that's the procedure. That's what happens when you want to take this limit. And so to see these Weil-Petersson volume polynomials arise, we just make a little observation, which I won't necessarily explain, but these top terms, so we've said that these...
So this replacement, this is essentially the q to equal 0 limit.
q to 1.
But the q to 1, this zeta function blow up, right? This zeta q.
That's right, but sorry, yeah, it's not...
And then in the q0 limit, this, like the ordinary zeta function should pop out.
It's what actually is happening is, so I guess I rubbed it out, but the fact says you're multiplying by this big power of lambda. So this big power of lambda is going to come and save you from the limit blowing up. Okay. Yeah. Okay, so what do we want to do now? I think all you need to do, these formulas are essentially the same, so all you need to do is tell me what this looks like in the limit. This sort of kernel out the front here. Okay. The other thing to observe as well, they look a bit different because, this is somehow a principal part at 0, and this is a principal part at 1 and at -1. And so my claim is that these top terms live at the principal part being minus, at 1. They also live at -1, but what I want to say is that you only have to look in a neighbourhood of 1, and then that's enough for you to actually extract these top terms. And then this factor B, that you actually see these Weil-Petersson volumes arise, factor B follows from a pretty straightforward calculation. Now hopefully you'll see why I'm using Z's and T's, because they're related. Z for me is at 1 plus T lambda. Okay. Right. So I'm comparing the sort of expansions of these sort of objects down here to do with Weil-Petersson volumes at T equals 0 with the expansion up here at Z equals 1. That's all. Okay. So the thing I need to look at is this 1 over 2y of z x prime of z. I want to take a limit as lambda approaches 0. There's lots of q's in here, remember? And actually there's a sort of lambda squared that we need, which will just come out and wash for us. This turns out to be, you could look at the expression I had up here and sort of try and see sort of what happens when you do it. This term out the front is going to kick in something very simple. That's just 1 over 4t squared. Then we see this exponential. And to get any contribution, you need this 2k here to match this m. Otherwise, you die in the limit. Okay. So, and as I said, these all of these coefficients that arise are quite explicit. This one turns out to be 4 to the k on k, zeta of 2k, t of the 2k. And do you know what that is? I mean, if you're following along, you can guess. Maybe you already know. This turns out to be, this is pi on 2 times 1 on t sine 2 pi t. Right, so log sine 2 pi, so log sine x essentially stores the zeta values. And this turns out to be, I guess what I was calling 1 over 2y of t x prime of t. So essentially what we've done is we've sort of taken this chunk here and taken this chunk here and said something like in the limit, these are the same. Okay, and that's enough to recover the Weil-Petersson volumes. Okay. Great. I think I can finish in n minutes for n small. Okay, so that somehow completes Jacchetto's magic square. So we sort of, but I think it's a sort of fun exercise in topological recursion which raises lots of questions. I want to sort of just talk quickly about some of these questions. So firstly, some of you will be sitting there and say, that spectral curve, I know that spectral curve essentially, and you'll know that there's going to be some relations to map enumeration. We know that essentially when you have something of this form, x is z plus 1 on z, I guess I read about this in Bertrand Nicolas' sort of one of their seminal papers, that this should tell you something about these coefficients. And essentially this is what's going to happen. This sort of counts genus G maps or ribbon graphs, whatever you like to call them, maps with, what are these B's telling us? Well, there are n faces, I'm going to leave a gap here, faces of degrees B1 through Bn. And, so I'll add in this word here, maybe pruned faces, sort of mean something to me, and internal faces with weights. So you can have like arbitrarily many other faces with weights. Yeah, and internal faces. Okay. And how do you get the weights? Well, you just look at what y of z is. Whatever it was, you try and write down what the weights are, and this is what you get. The internal faces have only even degrees. And they carry the weight. I'll call it, so say you have degree 2k, then the weight is this. So if k equals 2, then you have to do a little something different, and otherwise. A very sort of explicit infinite series in Q. Where the coefficients are essentially binomial coefficients. Okay. And I guess the expectation here is that this should give us some another way to see the Weil-Petersson volumes arise, because they should arise in the following way. What we have, because this is a combinatorial sort of count of maps, we have a tut recursion for maps. But now we're using these explicit weights. If we do something like take some limit here, I guess the expectation is that this should be some recursion for Weil-Petersson volumes. Now, if I say to you, to some of you, I say, tell me a recursion for Weil-Petersson volumes, you would say, well, look in Mirzakhani's paper. That's not what I want to look at. There's a sort of alternative, a simple form, which is Du's recursion for Weil-Petersson volumes. Then just to avoid any confusion, Do is not me, my name is Do. Can I have one more minute? Yeah? So maybe I just want to finish with some remarks. As I said, this is an exercise in topological recursion, but somehow what I like about topological recursion is somehow it's something that brings these sort of different sort of strands together and allows you to ask new questions. One thing we can do here is we can define, if you take these NGNs, they're sort of weird and they have these integer parameters, but you can sort of just take the top part. You just get this nice polynomial with these q zeta functions. So you can define what we're going to call q Weil-Petersson volumes. And the question I have is, what do they mean? You can reverse engineer a lot here. You can reverse engineer like Mirzakhani's recursion. You can reverse engineer the kernels that Mirzakhani uses. We haven't quite got there yet, but I think you can reverse engineer something like a Q-McShane identity if you know the whole story, and sort of take it all the way back and wonder, what is the sort of underlying sort of geometry going on there? You can ask, what do maps tell us? Right? Do you get anything? Do you get any mileage out of this? Maybe another proof that you see Weil-Petersson volumes, but we already knew how to prove that. I think there's something sort of possibly interesting going on here, because here's something that it's telling us, for instance. If I take the number of tilings of a 2k-gon, that's probably odd-sided, but let's say 2k-gon, I sort of want to tile it. So I'll get tilings, and they have to be even, so even degrees. Okay, I do this. I use these quotation marks means these faces in here pick up some weight, which is the weight I wrote down here, this Q series, and then I do some sort of normalization. Okay, this is the normalization that Raphael was asking about before. This should be essentially, maybe I have some extra adjective here, so some count of k-chord diagrams again. Where this Q is the number of intersections. If I say, well, why does this look interesting? Well, because the number of chord diagrams we saw is just some sort of finite thing. This is a polynomial, right? Some integer polynomial. What is the thing on the left? These tilings, of course, there are arbitrarily many. You can have arbitrarily many faces. So you can have arbitrarily many weights in there. Each weight is arbitrarily big as a Q series. So you just, and then you divide through by this crazy Q series, and you get a polynomial. I mean, there's something sort of weird going on. It's like this sort of, I don't know, like these tilings sort of like localize on chord diagrams or something strange like that, combinatorially localized. Let me just use some provocative terminology. And I guess hopefully you might think, well, maybe these tools could allow you to actually show that what we're calculating here has something to do with these double-scaled SYK correlators, which is the conjecture I sort of stated earlier. I'll finish there, thank you.
Questions? So prune, is that like tight?
Yes, it is like tight. So it just means that you don't see extra trees growing inside your boundary. Yeah. That's similar, right?
Simple?
Oh, maybe simple. Oh, sorry. Okay. Tight is that it's the shortest in its class or something. Yeah, okay, no. Then it's just that
I quite understand why you would get polynomials.
yeah, it's just like you don't like extra trees coming out here, so you actually see every edge counts to the boundary. In some sense.
So your spectral curve that you already erased looks almost like a theta function.
Yeah, it comes from the Jacobi triple product formula.
Yes.
So that's exactly where it comes from.
And if we'll make a modular transformation.
Oh, yeah, that's no, absolutely no idea. I'm not sure. Yeah, I'm not sure if I've seen it, and yeah, I don't know. Interesting. Yeah, I don't know.
I just wanted to ask about the conjecture. Is it is this if you take n equals to 1, and for this case, is it provable or or is it also a conjecture?
Is it true in the large N expansion? That's what you're asking, I think. Is it known to be true? I'm sorry, I need to think about this. It's, I don't think it's mathematically known. I guess it depends who you ask. I don't think it's mathematically known, but there is strong evidence for it. Yeah.
And then, just to understand the position of this, you have this matrix model with that potential, and you have this SYK model.
Mm-hmm.
Does the SYK model, if you take this double scaling limit, should also giving you the same expression, or if you take the same kind of observable?
Sorry, I missed that. Can you say it again?
So you have SYK model, and you have this random matrix model. I suppose the conjecture was for the random matrix model. You take this object, take the double scaling limit, you have the expression. Is it true for the SYK model as well?
I don't know. There is a lot that's been done for the SYK model, sort of previous to when I sort of entered the picture 1 year ago to the day, and there are sort of diagrammatics there. It is easier, like you can imagine it's easier, because if I asked you to calculate any particular one, you could do it with enough time. You just do it, literally do it. I'm not sure what the status is for matrix models. I think there might be considered to be dual to some matrix model, but I'm not. I can't remember.
Could you make precise what you mean by tiling?
Tilings. Anyway, maybe I have a square. So I'm thinking like I have a square on the other side, a 0, and I'm just going to sort of draw some sort of graph in here, but I need all the faces to have degree 2, 4, 6, 8, etc. My drawings maybe not going to be so good. Yeah, anyway, so something.
And on the boundary you have no vertices on the boundary.
On the boundary, yeah, so this is a 2k gone here.
Yeah, 2k gone
and that matches this sort of K here from the chord diagrams. That's fine. But yeah, they're infinitely many. There's an infinite sum. Each sum is an infinite series.
And you hope for a quantum curve?
Quantum curves have been solved, haven't they?
Usually things are easier in QDefunct.
It's
for algebraic curves. This is not algebraic.
Yeah, that's right. That's right. I haven't thought about it yet. It'd be good to think about.
Yeah, so last question. So back to the question of Kento. So did you try to rescale the spectral curve, this Okuyama spectral curve, in a way that this other spectral curve comes out? Not on the level of the computation, but like take the spectral curve, reparameterize it like multiplication by this double, what is this, Conformal symbol, I guess? Maybe square root of that or something like that.
To see it more directly?
Yeah.
Yes, I tried. This is somehow what came out of it.
Okay.
Yeah.
And does it work? Does it come out? Is it?
This is what could work for us, but I couldn't see it directly.
Okay.
Maybe it's possible. I'm not saying that it's not possible, but it was the first instinct is sure, just take the limit of the spectral curve, hope the limit works. But I don't know if I could see it.
Well, at least for 0 1, that's the answer, right?
Yeah.
In 0 3 it doesn't change because it's so the question is 0 3. Should work.
Okay. Any further questions? If not, let us thank the speaker again for that. Break of 20 minutes.